All right. Well, thank you everyone for showing up here. I know there's more people probably coming in here. Thank you for attending today's sessions. I want to introduce Mark from West Mountain Radio here for his DC power presentation. Mark?
Hi there, guys. We're going to talk today about a lot of DC power problems that people are typically having and what the state of the technology is and some of what the West Mountain Radio products are that can help you out in that area. Just making sure the screen works and everything. This is an outline of what I'm going to go through. There's a lot of details that I'm going to provide, a lot of charts and graphs. You can download the slides. There'll be instructions at the end of this presentation if you want to grab those slides and see what some of those charts are in more detail. I'm going to start out very simply. This is the problem we're trying to solve. The top chart there shows, give me 1 second here. My PC's being... that top chart is showing that if you have a light bulb, 6 watts, 50 feet of cable, you're going to lose less than 1% of your energy. But when you change that to a 60-watt spotlight, your loss goes up to 7%. And this is the problem that we're trying to run into in amateur radio because we're all doing high current kinds of things. Here's a chart that shows that same diagram we had before. We were using 12-gauge cable. If we switch that to 8-gauge cable, the loss goes down to 3%. Go to 22-gauge cable, your loss goes up to 67%. And by the way, well, actually, I think there's a slide for that. Where's the energy go? It turns into heat. It's not too bad of a problem if the heat is spaced out over 50 feet, but it's much more of a problem when the heat is concentrated in a small area like a connector or a switch. This is the chart I was referring to on the West Mountain Radio website. If you enter in the length of your cable, the current draw, it gives you an idea as what your power loss is going to be for various size cables. If you get the red indication there, that means the insulation is going to be melting off the cable. You probably shouldn't be using that size. A little bit about connectors. I'm going to start with the connector that you guys are probably familiar with in the lower right-hand corner there. You see that on some of the HF radios. What they've done is they've used 3 conductors for plus, 3 conductors for minus. So they've split their power loss between the conductors. And that kind of a cable, at 40 amps, you're going to lose almost 5 watts of energy. And I'm going to start talking about watts of energy that you're losing because you can kind of sense that. You know what a 60-watt light bulb, how much heat is being generated. So that 5 watts is probably pretty close to the limit of what that connector can handle before the plastic starts melting. Above that, we have the concentric DC power jack used on a lot of consumer electronics. 48 watts loss at 40 amps there. That's going to melt real quick. But even in the opposite corner, the banana jack, you're still losing a lot of energy. 16 watts at 40 amps in the banana jack. So those aren't even going to be that great for the high current kind of stuff that you're using. What we really recommend is the power pole connectors in the upper left corner there. The power pole connector, less than 1 watt of power loss at 40 amps going through it. That's just miraculous. So this is why we're really recommending the power pole connectors at West Mountain Radio. A little bit about power pole connectors. The 15 amp, 30 amp, 45 amp contacts, they're all interchangeable. So the shell is the same and you can plug any into any other one. There's no gender, no male, female connectors, so you can plug any power pole into any power pole. You cannot mate them incorrectly. You cannot put your plus and minus incorrectly as long as you've put the cables together correctly. We recommend crimping, not soldering, or at a minimum, if you really have to solder after you've crimped. The crimping makes a much better connection, much lower resistance connection than the solder will. They're UV safe, so you can leave them out in the sun. They're not going to deteriorate, but they are not waterproof. Switches, same kind of problems with connectors. You have a lot of loss over a small area. you want to be very careful with the switches. It's hard to find a good switch that's going to work for like 20 amps or 40 amps. I've got a picture there of one that's a 100 amp switch. That's what they use like in DC power charging stations for like automobiles. You can find 15 amp ones. I got a picture of one there, a picture of a 3 amp one, but they're really not as common as you would think. And you also have to make sure it's rated for DC, not AC. If you're looking for a problem, it's really easy to find your power losses by just measuring voltage drops across a connector, across a switch, or the entire cable length. Just key down your transmitter and then measure the voltage drop across there. I've got some examples. If you see a half-volt drop, for example, you're losing 10 watts in that connection. That's just a real easy way to just go through the station and find out if there's a bad crimp or something else has gone wrong. I'm going to cover a couple of situations. A lot of people call us with questions on grounding. What we have here is a station that's set up where you have an antenna at the top of a mast. Coax cable goes up to the antenna. We have a regular power supply that plugs into the wall at the base station. But the customer also has a weather station that he's got mounted onto the mast halfway up. And that weather station has a little, like a telephone wire coming down into it. And then that also plugs into the wall. The problem here is we've got two paths that the negative conductor goes through. One is up the coax to the antenna as you intend, but there's another conductor. It goes to the power supply, into the wall, into the weather station, up to that little weather station that's up on the mast, then to the mast, and then up to the coax cable. So there's two paths there to get from the antenna to the radio. When you key down, it's going to try and split that. And basically what happens is that little telephone wire will vaporize. Another situation, this is also very common. You have an amplifier in the trunk, and to save running an extra wire, you're using the very good conductor of the vehicle. So you connect the negative to the vehicle conductor, which is really good. It's a nice low resistance conductor. However, the problem with that is you're now sharing a conductor with all sorts of other components in the car. The spark plugs, the electronics, the radio, the computer in the car. So you've got a conductor that already has all this noise being superimposed on it, and now that noise is being superimposed onto your amplifier as well. So it's always best to run a second black wire directly to the battery from your equipment. Talk a little bit about batteries. Always fuse the batteries. Near the battery is good. It doesn't have to be a good-sized fuse, 50 amp, 100 amp. You just want something that if you accidentally put a screwdriver across a conductor downstream somewhere, the battery doesn't blow up. Instead, the fuse goes. So it can be, like I say, a relatively large fuse. You just want to make sure that it blows in case something goes wrong. Use sealed, not the wet batteries. We recommend this primarily because you're usually nearby the battery for amateur radio. A lot of times you're transporting the batteries and that acid can spill. So that's primarily why we're saying use the sealed batteries, not the wet batteries. Don't put the batteries in an airtight enclosure. Even the sealed batteries do vent some gas. It doesn't look like they do, but they do. So you don't want to have them in a completely sealed container. It's okay to have them indoors. It's okay to have them, in a closet or something like that, but you don't want it in an airtight container. And for disposing batteries, Batteries Plus, I believe, will take the batteries for you. Flooded lead acid batteries. This is the type I told you probably not to use. I'm just going to go through the different technologies so that you understand the difference between the batteries. In the flooded case, we've got the two plates. You pour in some acid, and you have yourself a battery. The sealed batteries that we talked about are similar, but what they've done is they have these acid patties between the plates in the battery. So there's these patties of acid put in between there. So you don't have the thing filled up with acid, but basically you have these pads that are filled with acid between the plates. I want to talk about a starter battery real quick. What they do in the starter batteries, in the old days they would drill holes through the plates. Now I think they use kind of a steel wool paste. What they're trying to do is they're trying to increase the surface area. If you have a lot of surface area on the plates, you get a lot of instantaneous power. You've heard the advertisements where they talk about cold cranking amps. The cold cranking amps is higher if you have a lot of surface area on the battery. The problem with that is, if the battery is not fully charged, that surface area corrodes very quickly. A car battery is typically always charged up. You use it to start your engine, and then you immediately start charging it up again. So it's not as much of a problem. But because of that huge amount of surface area, these batteries are not going to be very good for amateur radio. Even the hour or 2 hours when you stop talking and then before you drive home and you're going to start charging it up again, you're going to have a lot of trouble with these kind of a battery. These are the cheap ones that you're going to see at the stores because this is what everybody's buying for their automobiles. But you really probably don't want to be using this in amateur radio. I skipped ahead there. This is a depth of discharge chart. What it's showing you is for a given number of cycles where you discharge the battery and charge it back up again, how many cycles you can get out of the battery before the battery stops working. So for example, in this chart, if I go down to 50% of the battery capacity, charge it back up again, go down to 50%, charge it back up again, I'm getting like 1,200 cycles on the battery. If I go all the way down to 80%, then like 600 cycles on the battery. This is just the way the lead acid batteries work, and then we're going to come back to this depth of discharge chart a few more times. I want to talk about AGM real quick. The AGM batteries are a little bit different. Instead of those patties between the plates, they have these little fiberglass envelopes that they slide over the plates. The manufacturing is cheaper on the AGM battery, and it's a little bit lighter weight. And here's the depth of discharge chart on the AGM. The orange line there is the AGM battery. The blue line is the lead acid. So the lead acid battery does much better. Much better as far as the depth of discharge goes. The AGM is a cheaper battery. It's a lighter weight battery. So it's probably better suited if you're using it, for example, on a base station where you lose power 4 times a year, as opposed to if you're going to use this battery every weekend to drive up to the mountainside and talk on your radio. Just as a comparison, we were talking earlier, the 50% on the standard lead acid battery, you get 1,200 cycles. You're getting, what, 200, 300 cycles at best out of the AGM battery, even going to just the 50% level. This is a discharge chart. The red line shows you how a lead acid battery discharges. AGM standard lead acid is pretty close to the same thing. So as the battery is going down, you can see the red line goes down to nothing. I'm getting 93% out of this battery. It's really hard on a lead acid battery to get the same number that you stamp on the side of the battery out of the discharge. You have to charge it up at just the right temperature and discharge it under just the right conditions. So this particular test, I got 93% of the battery capacity when I discharged it. However, that blue line there shows the 11.7 volt line. 11.7 volts is important because that's the minimum voltage that you need to transmit. So if I look at that line, I have to stop transmitting when the battery has hit the 66% level. So that's more of a problem. And then that yellow line that I've got up there represents typical losses from cables and connectors and stuff in the station. So I'm really only getting 39% of the battery capacity out of that battery. This is, like I say, a typical lead acid. This is the same curve, but what I've done here is I'm done cycling between transmit and receive. So I've got like a 2 amps for 30 seconds, and then 20 amps for 30 seconds. And then I repeat it, 2 amps, 20 amps, 2 amps, 20 amps. And this shows what that looks like. You can see every time I transmit, the voltage drops a little bit. So I'm actually, the blue line, I'm only getting 35% out of the battery. And if I use the yellow line, I'm only getting 12% of the capacity of the battery out before I can no longer transmit. That's with a typical 100-watt transmitter. I'm going to talk about lithium batteries a little bit. First thing you think about is they explode, they start on fire, whatever. There's a lot of stuff in the news about the lithium batteries. I've been going to battery conferences for a long time and listening to the people talking. It seems like they've pretty much given up at trying to find out the full why. The customer base seems to have accepted it. They're saying roughly 1 out of every 100,000 cells is going to have a thermal event, and that's going to cause some sort of a problem. And they're relatively happy with that as far as the electrical vehicle goes, because they say that gasoline cars start on fire more often than that. So take that for what it may be. There's a pile of different chemistries out there, and it seems like every 6 months there's a new chemistry that somebody's proposing or trying or whatever, and then they disappear a year later. These seem to be the popular chemistries at the moment. The ones that have iron and phosphate in it at the top there that have got the blue arrow on, that seems to be the best combination for amateur radio use, at least right now. And there really doesn't seem to be anything close on the horizon. Like I say, people come up with this wonderful chemistry and then it just sort of disappears. But right now, the iron phosphate seems to be the best. They call it relatively safe. Their definition of safe seems to be if you pound a nail into the side of the battery, are you going to survive the event or not? So for what it's worth, I think you probably want to stick with the iron and the phosphate combinations, even though they're a little bit more expensive. The depth of discharge on lithium. This is where we really shine. We still have the same blue and orange lines for the 2 lead acids that we talked about. The green line is the typical lithium charge. That 50% mark that we were talking about earlier, you're getting almost 6,000 cycles on the battery, is what this depth of discharge is showing you. Another impressive thing, you can go all the way up to 100% of the capacity of the battery. The lead acid batteries, you really don't want to go below 80%, but you're still getting 2,000 cycles out of that battery even if you run it all the way down to 100%. So this is extremely impressive. Temperature, not quite as impressive. The lithium batteries don't like high temperatures. If you run them constantly at high temperatures down the south, outside, that kind of a thing, you're going to lose life and capacity. But also, they don't like being charged or highly discharged below freezing. So the lead acid batteries are far more tolerant on that. In fact, I don't know what it probably is not good in the life, but the lead acid batteries, you can actually get more capacity running at a higher temperature. Here's the transmit-receive cycling that we did earlier. This is with the lithium battery. What we're showing here is that even on the yellow line, I'm getting 76% of the capacity of the battery out of that lithium battery. The blue line, 92%. And most of the lithium batteries always come out to at least 100%, often better than 100% of what the stamped rating is on the battery. The reason that this is you can see the voltage is dropping way slower on the lithium batteries than it was on the lead acid batteries. So you're staying well above that 11.7 mark for a lot longer on the lithium batteries. This is making the lithium battery sound pretty good. I'm going to talk just a bit about charging. A typical charging algorithm goes through several cycles. The first cycle, you put in a fixed current and you wait for the battery voltage to get up to a certain amount. And then you hold the voltage at that amount and let the current drop to a certain amount. And then on a lead acid battery, you allow that current to just keep going at the relatively low amount. That's the trickle charging, the maintenance charging that they talk about. The lithium battery is the same for the first 2 cycles, but as soon as you get down to 0.05 C on the charging, you want to disconnect the charger. You don't want to put any more energy into that battery. So that's a big difference between the 2 algorithms. And the reason I'm mentioning that is it means you can't use a standard lead acid charger on the battery unless the battery has electronics in it that can tolerate that. And what that electronics does is it automatically disconnects it when it detects the trickle charge. But you have to be very careful about that. Either use a lithium battery that can tolerate a lead acid charger or use a charger that has been designed for lithium use. I just did 2 charts with 1 little speech. Cost comparison here. If you're only doing receive only, The lithium is going to be much more expensive. It is a more expensive battery. However, if you talk half of the time and you're doing 100 watt FM, the costs are very similar. So if you're doing a high current draw on the battery, the lithium batteries, and I'm taking into consideration the lifetime of the battery in this, you're going to get a lot more out of your battery. There's a calculator that we have online that'll help you figure this out. Tell it what mode you're using, SSB, CW, whatever. Tell it what percentage of the time you transmit, and it'll put some various batteries up there and give you a comparison as to how many hours of talk time you will have. I'm sorry, not talk time, actually use time you'll have with that battery. So that's a calculator you can just find on the West Mountain Radio website. Battery weight, this is another place lithium really shines. 6 amp hours per pound versus, what, 1.25 amp hours per pound. So the lithium battery is very light. I'm going to talk about battery boosting here for a moment. What the battery booster does is it takes the normal discharge chart, which is blue this time in the upper left corner there, and it boosts the voltage up so that you get a constant voltage out. So even though the battery might be going all the way down to 10.5 volts, you're still getting 14 volts or whatever you want out of the booster, which is good enough to run the radio. So this is an alternate to using, for example, a lithium battery. You can still use your old lead acid batteries and get more life out of them. Here's a little bit of a chart cost comparison. The lead acid battery, maybe $300 for a 74 amp hour battery, and you get 10 hours of transmit time on that kind of a battery. A similar lithium battery would be like a 40 amp hour battery, $360, you get the same 10 hours. Now, if you use a 74 amp hour lead acid battery with a booster, you get 15 hours out of that battery. You spend the same 300 for the battery, 250 roughly for the booster. But that 250 you get to use over again on your next battery. Similar to that would be a 60 amp hour light bulb battery, and you get 15 hours out of that for about $570. So this gives you a little bit of the cost comparison as to whether a booster might be better for you or whether a lithium battery would be better for you to get the additional talk time. A little bit of a history on the West Mountain Radio. Dan wrote an article in 2004 on a unique battery boosting idea that he had. His father was an active ham, and he was an engineer for switching regulators. So what he did is he designed a booster which was very low RF. And what he did is usually a switching regulator will convert the voltage to AC and then back to DC to get the voltage. What he did is he took the voltage that he had, say 10 volts, and then he did switching on it, and then added just an additional 4 volts or whatever to the 10 volts to get his full 14 volts that you might want on the output. So the amount of energy that's being switched is far less because he's passing through that original 10 volts. That makes a huge difference as far as the RFI goes. So these are very quiet units. He didn't want to manufacture it, but there are so many people that responded to his QST article on this idea that a friend of his, Tom, decided to set up a thing where they actually worked together, and he did all the manufacturing on it. They were selling these for a number of years. In fact, West Mountain Radio had always, when they were asked about battery boosters, were recommending these. Tom died a few years ago, and when that happened, we talked to Dan and made an agreement to redesign his unit so that it was more producible for us. Tom had been building these things by hand. So we put in surface mount components, made it smaller, and instead of a whole pile of models, we have just one model, a 40 amp model. And it's been working out really well for us. Unfortunately, COVID has hit and kind of thrown a little bit of a hiccup in that production line, but it's been a very popular product. It's been working really well for us. I'll talk a little bit about battery testing. Typically what you can expect is 2 to 10 years out of a lead acid battery. That's a big range. 2/3 of them die by age 7. 5 good years if you use the battery at 77F, more like 3 years at 90F. Typically what the battery manufacturers will tell you is when there's a 20% drop in the capacity, some battery manufacturers say 15%, at that point it's going to start dropping a lot faster. So that's the point where you need to know that that battery's about done. Two big causes for the batteries is corrosion. And the corrosion happens when the battery's discharged. We talked about that a little bit earlier. But even if you're not using a starter battery for a car, just any battery, if the battery's discharged, the plates get corroded. And the longer they stay in the discharged state, they corrode longer. So if you let a battery discharge and then you let it sit on the shelf for a month, that battery is going to be in very poor condition because it'll just sit there and corrode. But even if you try and keep it up, keep it charged as much as you can, you're still going to get some corrosion, and that's probably the major cause that the batteries are going to die, the lead acid batteries. The next biggest, that orange area there, is what they call dry out. I talked about the venting. When you charge it too fast or you discharge it at a high rate, and in amateur radio, again, it's kind of hard to avoid discharging at a high rate because that's kind of what we do. Then you lose a little bit of gas. Again, it's not a lot of gas to hurt you, but it's a little bit of gas that gets vented. And that gas contains acid that's not replaced. So eventually, there's just not enough acid left in the battery for it to do its thing. So that's dry out. This is a narrative of what I just said. Two popular test methods. One is you measure the voltage under load. You take your car into the shop, you ask them how good your battery is. They put a giant load on it, figure out how much the voltage dropped. Essentially, they're measuring the impedance of the battery, and they determine whether the battery is good or bad based on what the voltage drop was when you had some sort of a load. The other way of testing is a true capacity test. You basically run the battery all the way down, measure how much energy came out of it, and then you know how many amp hours the battery was. With those two methods, if you're looking for a detection of the corrosion, voltage under load detects 100% of the time. It predicts that the battery is near death about 95% of the time. For dry out, however, the voltage under load doesn't work very well. It can tell you that there's a problem 15% of the time, and it's no good at all for predicting that end of life is near on the dry out. So when you calculate all, the true capacity is 100% time detecting, 95% predicting in both. When you calculate everything out, the true capacity is really the better way to go, although the voltage under load gets you where you need to go 3/4 of the time. West Mountain Radio sells a true capacity tester. We call it the CBA, Computerized Battery Analyzer. Basically, it's an electronic load, connects up to your computer. You can use it for a lot of different things where you might need an electronic load. But in the case of battery testing, it runs the battery down. Those charts that you saw earlier, the discharge charts, those all came from our CBA unit, where you wanted to simulate receive and transmit, where you wanted to just simulate a discharge. This is what one of the charts looks like in the CBA. You can run multiple tests over time, like on the same battery. You can kind of tell when the battery gets to a point where, hey, now there's suddenly this big difference and I'm getting a big drop in capacity. You know it's time to get rid of the battery. We have extended software, which allows you to do some of the fancier things. That's additional money for the extended software. It lets you do the multiple discharge test, which is the 20 seconds on, 20 seconds off kind of a thing. We can make this thing look like a constant resistor. Say I want this unit to just look like a 2-ohm resistor. There's a lot of other fancy things in the extended software. We've got a lot of different models. Our most common model there in the upper left is the 150 watt model, the CBA5. You can actually go up to 200 watts for short tests, like 40 minutes or less. But that primarily what we're looking at is how much energy we have to dissipate in the unit, so that we've got the different size units. We've got 1,000 watt units, 2,000 watt units. If you're doing coin cell batteries, we've got a smaller unit for just 10 watts. So there's a lot of different combinations that you can use on the CBA. It's all the same software. I want to talk a little bit about one interesting application with the CBA. We have another product called the Power Check. And the Power Check is basically just a voltmeter, amp-meter, but it has an internal log in it. So you can put it in line and actually measure the current draw of your product over time. So for example, let's say we use it in a model airplane or a drone or something, and you have this thing do a takeoff, you have it do some sort of a flight test, and then you have it do a landing. You've now saved in the log how much current the unit drew in each cycle of its flight. And you can take that, put it in on the bench, and actually feed that data into the CBA, and the CBA can replicate the same load on your battery on the bench. This will give you an opportunity, for example, to test several different brands of batteries to see which one handles the type of cycling that you're doing on the battery for a real-life situation. So this is just an interesting marrying of two of the West Mountain Radio products. Uninterruptible power supplies. The PowerGate PG40S has been a very popular product from West Mountain Radio for many years. Basically, I'm showing here with diodes what's in there. It's basically, you can either take voltage from the battery or from the power supply, whichever's a higher one is going to go through the diode and power your radio. And while the AC is connected up, there's also a smart charger in there which will charge the battery. One of the questions a lot of people ask is, can I connect two batteries in parallel? It's okay as long as the batteries are the same age and the same amp hours. What you want to do is periodically remove one of those straps and just see if there's current flowing between the batteries. Less than 1/4 of amp is not going to be a big deal. But you don't want to get into a situation where one of the batteries is going bad and the other battery is spending its whole life charging it. A little bit about solar panel. Just to give you an idea of the size of the panels, I've got some sizes in here. 100 watt panel, for example, is 43 by 36 inches. This is just to give you an idea. If you search around on the internet, you seem to be able to find panels that are roughly $1 a watt. Fancier ones, with stands that fold up, that kind of a thing, more like $2 a watt. And I'm not talking about charge controllers or anything, just the panels themselves. Solar panels are a little bit interesting in that the amount of power that you get out of the panel depends on how much current you're drawing. This chart here, again, we use the CBA to get this chart. What the CBA did is it sweeped the panel, 0 amps, 1 amp, 2 amp, 3 amps, and as it's going up, it's plotting how many watts it got out. You can see that the panel has a sweet spot there, right around 5 amps or so. You're getting the maximum amount of watts out. And that, by the way, is what they call the maximum power point for the panel. The charge controllers that they sell with panels, they find that sweet spot and then convert the voltage, whatever voltage they're getting out of there, to what they need for whatever they're doing, charging a battery, for example. This is the same diagram. If you look very carefully in the lower left corner there's a mini version of the big one. The big one is when I'm pointing the panel at the sun. The little one is when I'm pointing it at the north sky that's bright but doesn't have the sun. So this gives you an idea of the difference that you get with sunlight. It's not just light. You just don't want to get the panel lit. That sun makes a huge difference in the amount of energy that you're getting out of the panel. One of the things that you have to take into consideration is the sun moves. So you want to work that into your formula. So people want to use solar panels in their station. If you have the PG40S, the older style power gate, what you can do is you can connect the solar panel to a charge controller to the battery and put that in parallel with the PG40S. That will all work together. It's typically good, it's typically okay to connect two battery chargers in parallel together. You cannot connect battery chargers in series with each other, but in parallel they generally work. I should point out that the MPPT controllers are notoriously noisy, so you're going to get a lot of RFI, which is why we came up with the EPIC power gate. The EPIC power gate, we added an MPPT controller inside the EPIC for solar, and it's designed for radio use. It's not very noisy, and it also uses FETs instead of diodes. I have diodes on the diagram here, but those are effectively FETs for very low loss drops. So the EPIC has added a very low loss drop. Instead of a diode drop of about 1/3 of a volt, we're now got a 50 millivolt FET drop. And we've got the MPPT charging in case you want to use the charger. You don't have to, you can just use your regular power supply with it, but you've got that option in there. That's the presentation. Do we have any questions?
Okay, my question, okay, very good. Thank you. My question is on if you have the same battery with a brand name from a big box store and from a place that generally sells batteries of various types. I've heard the place that has the batteries only as their main product versus a big box store, the batteries are different. The big box store generally is not as good. Have you ever tested that that idea? Thank you.
Are you saying the same brand battery?
Yes, the same brand. Brand A, and it's sold at both places. And I've heard that the place that sells batteries alone as their source of income, I've heard them telling me that their battery generally is better than the one come from a big box store. Have you ever tested that at all?
What we know is you have to look at more than the brand. Definitely some brands sell specific batteries to specific stores. For example, at Walmart, for example, they might have a battery that actually is not being sold by anybody else, even though somebody else has the same brand name. You have to look at the entire part number. And the part numbers of there's a lot of variation in the part number. So we talked about the starting batteries earlier. You're going to be able to get a battery with a name brand that's actually intended for starting a car battery. And it's going to have the same brand name on it in a different situation, for example, for marine use in a deep cycle kind of a situation. So you have to look very carefully at the part number. I've not seen a case with the same part number battery from different sources is going to be different. But you do have to look at the part numbers carefully. And a lot of times you can find the specifications for the battery, the full spec sheets online if you do a search on that part number. Some of the companies are really good about it. Some of them try to really hide that information, but look at the full part information. Stay away from starter batteries. If they're advertising it for use in your car, I'd be very suspicious. If they're advertising it for use for like a trolling motor in a boat, the marine situation, that's going to be a good battery for you because that's the kind of situation you're using it in. You're running it down, and then you're going to charge it back up again and run it down again, as opposed to an automobile where you're just going to use it for a little bit and then charge it back up again.
I have a question about charging lithium batteries. Supposedly they're not supposed to be charged below certain temperatures, right? So you can use them at low temperatures, but you cannot charge them at the same low temperature. How do you deal with that?
Usually the batteries have electronics in them that will prevent them from being charged when the temperature is too low. A lot of times you're using the battery in amateur radio in the same location that you are. You're going to have it in the cab of the car, and you're going to be in the cab of the car. It's not as common that you're going to leave it out in the cold. But yeah, you can't charge it at too low of a temperature, and the battery should have electronics in it that prevents it from charging when the temperature gets too low. Most of the batteries have a lot of electronics in there to prevent from lots of bad things from happening. But the temperature is one of the primary things. I've seen that even in the real small lithium batteries that they use like in toys and stuff, where they've actually got just a simple little thermal switch in there of some sort that prevents the battery from being used when it's too low of a temperature.
Another question I have is for supercapacitors. So instead of using a battery which is turning electricity into chemical energy and then back from chemical to electricity, can we use a massive supercapacitor which is, it's big, it has even lower power value per weight ratios than lead acid batteries, but it can be charged million times with very high currents, can be drawn with very high currents. Do you have any solutions for that? Like, for example, I would charge it to, I don't know, let's say 20 volts or something like that, and then as it draws down to 10 volts, you keep a steady output at 13.8 for the radio.
Well, in theory, you could use a booster for something like that. I have not seen supercapacitors that are large enough, though, to support something, for example, for like a radio transmit. The typical uses that I've seen for the supercapacitors are very low current applications. Keeping a clock running or whatever for months on end or something like that. Yeah. I don't have any experience with the supercaps that are that big that are going to be able to handle that kind of a current. But if it's just the boosting, the standard booster that we have would work, if that's all that the problem is. Are there any other questions? Well, thank you guys for coming then. Remember, you can, whoops, let me just put that on there. If you're interested, you can grab the slides up there or come by our booth and we can write that down for you too. Thanks.
All right. Well, thanks everyone. Mark, thank you, and we definitely I learned a few things there, which is always good. Stay tuned. We're the ARRL is going to have a forum coming up here next at 2 o'clock, and we're going to have a question and answer. There's going to be 5 gentlemen up here from the ARRL that you can ask questions of. So definitely come by and get here. It should be an interactive experience, and we'll look forward to having that discussion here in a few minutes. Thank you.